In this video I'm going to illustrate vectorization with a simple problem. So the problem is that we have two arrays, A and B, and we want to find for each element in A the closest element in B. So here I have generated some elements and put them into A and B, and I made sure that they have some common elements because this introduces some edge cases later when we do the binary search. So we're gonna solve this problem in three different ways. So the first one is going to be just two nested loops, which I'm sure that everyone who is watching this video can write without any problems. Then we're going to write the vectorized equivalent of the two for loops, and then we're going to write the actual proper solution, which is basically you first sort B and then you do binary search for every element in A, and you do this binary search in parallel for all the elements in A, which is going to be the fastest solution. Okay, so this is the sort of the map for the video, and let's quickly write down some stuff here. So basically we want to iterate over all the A elements, and we're going to, for every A element we're going to maintain an index of the closest. I'm going to initialize it with 0, and then for every B element I just check if the current BG element improves the current index of the closest, and if it does, we just update. Then we just update the index of the closest, and then we add it to the A closest. Okay, so because this is going to take some time, I'm actually going to wrap this up in a TQDM notebook so that we see the progress, and I'm going to speed this up when I show the video because it's going to take about 3 minutes. So yeah. Alright, so it's done. It took about 3 minutes. It's really slow, so we're obviously not going to use that whenever we encounter this problem in real life. So, okay, what can we do here? So if we think about it, what we're doing at every iteration is, for a fixed element in A, we're basically finding differences to all the elements in B, taking their absolute values, and then we are taking the argmin of that. In fact, let me quickly show it. I'm just gonna, okay, so we have 53 index, and the first element in A is, oh, it's actually 0. So let's show it with the second element, because yeah, it will be clearer if it's not 0. So yeah, okay, so we have this element. So what we're doing essentially on an iteration is basically we're doing this. So we're taking this difference, we're taking the absolute values, and then we are doing the NP argmin. We're taking the argument which produces the minimum. So you can see it's doing exactly the same, but obviously, it's a lot faster because it's in NumPy. And basically the idea is to build a matrix where all the columns are for particular A element. So in this matrix, in a given column, all the A elements would be the same, and it would be combined with all the B elements, and for the rows it would be exactly the opposite. For the rows, the B element would be fixed, and we would subtract it from all the A elements. So if we wanted to do the reverse problem, if we wanted to find the closest element for every element in B to every element in A, then we would have to just take the argmin over the rows, not the columns. Okay, so let's quickly implement this. So let me just remove this stuff here. So first we want to repeat the A element B times, right? Let me see how this one goes. Oh yeah, but we want the shape to be a matrix, so we're going to add a dummy dimension here before we do that. Okay, so if we now see the shape, it's the length of B times the length of A. Alright, so let's do the same now for B, and then we're going to subtract them, and we're going to be halfway there actually. Okay, so we're doing the same thing here. Right. Oh, and you can see actually that we have to transpose them because they're in different shapes. Right, so let's transpose B and take the absolute of that, and let's name this diffs. I'm going to later move this into a single cell so that we can see how much faster it is. It's going to take a few seconds still, but yeah. So if we now do the argmin of the diffs along the 0th axis, let's name this Cartesian, A closest Cartesian, because this matrix is basically a Cartesian product of A and B. Oops, missed a G here. So now have a look at Cartesian and see closest. Yeah, I mean, eyeballing them, they look the same, so let's just do the following. Let's take their difference and take the absolute values, and let's count the non-zeros. Oh, that's a section without a mess. Okay, so all the elements are 0, so basically this method is exactly the same as the one that we did above. So let's move everything to a single cell so that we can measure it. Okay, let's delete some cells, right? And now let's wrap this in time. Actually, do I have it imported? I have it. Alright, so let's see how long it's going to take. So 5 seconds, a lot better. And now we're going to have a look at the fastest solutions. The fastest solution. Alright, so let's now do the fastest solution. So I already gave away the idea. The idea is that to just sort B first, because we're going to do a lot of searching in there, and then just do binary search. Now, binary search is not going to actually return us the actual closest element. It's actually going to return us an insertion point. So you can see here that the default is left-sided binary search. So this is going to return us, an index, and it's going to be either equal to the index that it returned, or it's going to be the closest element. Actually, is going to be either the one that is located where the index is returned, or where the previous element was, right? By the definition of the left-sided binary search. So basically what we want to do now is we want to create an array of the left-shifted elements and one array with the non-shifted elements, and we want to stack them together and find the differences for every single A element to the two possible candidates. We can do this vector in a vectorized way because we're only working with vector here. We're going to have a vector for the left-shifted elements and the one for elements that are not shifted, and then we're going to just apply an argmin along this axis, and we're going to find for every element, we're going to find a vector that tells us for every single element, is it closest to the left or is it closest to the one that is directly returned from the binary search. And then we would just have to set the indices accordingly. So so let me demonstrate that real quick here. So first we need to sort B. All right. Then we will find, then we will find the insertion points by doing a binary search using the indices that we found in the previous step. So we have the indices here, right? That's great. Okay, so we have this, but actually binary search can, if the element that we're looking for in an array is actually bigger than all the elements, the index returned would be actually bigger than the, it would be equal to the length of the array, so it's actually going to be an invalid index. So we want to say if we have an index that is not a valid index, basically. So let's see if we have elements like that. Oh, actually, in this particular case, it just so happened that we don't have elements like that, but in general, it could happen. So we want to basically decrement those. So if we have an element in A that is bigger than all the elements in B, then the closest element to this element that we're looking for is the last element in B, right? So that's essentially what we're saying here. Cool. So now let's build the left-shifted array that I mentioned earlier about when I talked about the binary search. So let's start up with just creating a copy of the indices. Then we just subtract 1 to create the left-shifted elements, and then we have to take care, for those elements that were closest to the 0, we have to zero them out. So because they would become -1 after we shift them to the left. So now we have to build the diffs. So for this, we just subtract like this. J sorted B, left shifted, and we want to do the absolute value of this. Right, so we have the left diffs, and then we do the same for the normal diffs. Cool. So now we just have to stack them. I already googled that, so I'm just gonna save myself some time now. So we just stack them like this. It's basically the same as zipping in functional programming, but since it's in NumPy, it's a lot faster than converting them to lists, zipping them, and so on. Yeah, we have to, after we stack them, we want to take the argmin along the second axis. Okay, so let's have a look at the shape of this thing, and yep, it has the same length as the A shape. So that's cool. This tells us basically the closest element. So here we are selecting the closest element for every single element in A. And now we have to finally build the actual answer. So the closest indices, we have to just first copy the normal indices, and then we just select wherever in the closest indices we selected the left one, we just take them from the left, we just take the answer from the left shifted. Okay, so like this, and we don't have to write the same thing for the non-shifted, so this would look like this. We actually don't need to do this. So those would be just the one from the indices like that. We actually don't need to do this because we copied the closest indices from indices array anyways. So yeah, we do this. Let me see. Closest indices. Array cannot assign. Mask is true. What? It's actually kind of weird. Let me see if the shapes are correct. That's kind of weird. Oh, I have actually, yeah. I've actually got the broken one here. I mean, I've taken the, yeah, the mask is not binary basically. Okay, so, whoops, that was a little mistake. It's okay. So now we have the closest indices, and if we apply them to the B sorted, then we would have the same elements as the ones that we have in, that we found in the previous step. Actually, not necessarily exactly the same, just they're both the closest. So to compare them, let's find how far B sorted B closest indices is to A, and let's subtract that to the absolute value of the same thing basically. So the Cartesian A closest minus A. Okay, so we have this thing here, and now let's count the non-zeros. So we have no zeros, no non-zeros. This basically means that for every single element in those arrays, they're they have the same value. So let's now put this all into a single cell and wrap it up in a time so that we can see how much faster it is compared to the other two solutions. And it's kind of neat also. I think this one is the most elegant solution. Yeah, and that's about it. So let me run this up in a time. So yeah, you can see, it's a lot faster than the previous solutions. So if we just divide this by hand, yeah, it's about 300 times faster than the other two solutions. So yeah, that's kind of it. Thank you guys for watching, and I'm kind of, I'm obviously very new to this YouTube stuff and talking in front of an audience. So if you have any questions, comments, let me know, and I'll see you guys when I have something cool to show in some of the next videos. So see you guys.